potential energy practice questions. Let's have a look at some of these. As you can see, this is our first one. Let's label appropriately first, an appropriate label for the X and the appropriate label for the Y. Our potential energy is going to be on the very side, on the Y-axis, and then our reaction progress is going to be on the X-axis. Next, the activation energy for the forward and activation of the reverse. You should know by now that those are always in reference to the activated complex. See the previous video on collision theory, as well as the activation and potential energy videos that goes into detail about this. So whenever we have the activated complex, we reference that to, let's say, our reactant first. So this is our reactant. So you find the difference between that. That is going to be your activation energy. And this has to be obviously in the forward reaction, because obviously we're dealing with a reactant. We're going left to right. So this here is going to be our activation energy. Okay, and it's going to go in the forward direction. So this here is, this here is the correct analogy here. Next, we have the reverse. So the reverse is always between activated complex and the product. So this here is your product. Okay, we can kind of show it to you here. So the difference between that is going to be your activation energy. This is just going to be of, the reverse direction. Okay, let's answer the questions now. Our delta HR, by the way, delta HR is always going to be the difference solely between the reactant and the product. Okay, so this here is our reactant. This here is our product. We just find the difference between that. That is going to be your delta HR, okay, your enthalpy, your change of energy. Next, we have A. Is the forward reaction endothermic or is it exothermic? Okay, so obviously forward is what we're referencing here with the reactants. We're going left to right, okay? So it has to be obviously endothermic, because we had a certain amount of mass here, we have a certain amount of mass here, but the potential energy within that mass, right, has increased, right? Obviously based on the law of conservation of mass, right? It cannot be different, right? What happened? Why is the potential energy higher? It means energy was added into it, okay? So energy came in. So hence why it's endothermic. That's why the potential energy increased, okay? So obviously this here, A, it's going to be endothermic. We have taken in energy, okay? Another way you could also say it is based on the activation energy, okay, referencing. So if you have your activation energy and it's reversed and that is greater than your activation energy for your forward, this means that this is going to be an exothermic reaction, okay, an exo. However, that's not what we see right now. We see this activation energy of the reverse, we actually see it as being smaller. Okay, so it's actually this way. So if it's smaller, that means it's not exothermic, it's going to be the opposite, it has to be endothermic. Hence we have endothermic, okay? Next we have B. Which has the higher potential energy, the reactants or the products? Obviously, we can tell based on our metric here for our potential energy, our products are much higher. Okay, so obviously products is going to be the answer for that. All right, our next question. Use the potential energy diagram below. Estimate the values for EA forward, EA rev, and delta HR. Okay, so we have our reactant, we have our product. As we can see here on the side, it says each pair of the hatch marks. Okay, so between like this and this, and this and this, and this and this, and this and this, right, is 5 kilojoules. So every time we go up, we're going to go up by 5 kilojoules upwards, right, of it increasing. So is the reaction endothermic or exothermic? Okay, well, we can just first see 1, 2, 3, 4, 5, 6, 7. Okay, between 7 and 8 over there is where we kind of see the reactants belonging. Okay, so I counted 7 over here. We haven't necessarily hit that 8th one. Okay, so we'll just do 7. Okay, and we know that each notch, right, each hatch mark, okay, as it goes from one to the next is 5 kilojoules. Okay, but remember, it's not 7, okay, it's 7.5. It's not necessarily 8 over there. Okay, the green is a little bit under that. 5, it's going to be just 5 kilojoules. Okay, so you're just going to use your little calculator, see what number you get. You end up getting 37.5 kilojoules. Okay, so 37.5 kilojoules. Now that is for the reactants. Okay, that's how high it is. However, the product, what is going to be the difference for that one? Okay, for the product, if you were to just kind of elongate it, again, I'm not using a ruler over here, but if you were to be as straight as possible, okay, it's kind of in between, you know, the second and third notch. I'm just going to give it a rough, 2.5. Again, we're just going to times 5 kilojoules, okay, and then that should give you 12.5. Okay, so you get 12.5 kilojoules. So this here is going to be at about 12.5. This one here is going to be about a 37.5. Okay, we can obviously find the difference between the two. Okay, so this is reactant and this here is our product. You find the difference between that. You just do 37.5 minus 12.5, getting 25. Okay, so my delta HR here is going to be 25. All right, how about our activated complex up here? Because we still have to find our activation energies. We're always going to reference the activated complex. So if this here is our activated complex, we can just keep on looking up. So this is 7, 8, 9, 10, 11, 12, 13, 14, 15. Kind of looks like it will be at a 16, right? Maybe about a 16 over there. Okay, so that would be 16. So let's write that out. 16 multiplied by 5. What would you get? Ended up getting 80 kilojoules. Okay, so we got 80 kilojoules all the way up here. Okay, so if that is the case, then how would we find our EA of the forward reaction? Okay, so I'll just write this here, EA of the forward reaction. Well, we have our 80 over here, okay, but we got to subtract it by our reactant. We figured out that our reactant was 37.5, so I'll just subtract it by 37.5. Okay, what do you end up getting? I end up getting 42.5 kilojoules. Okay, so this over here, our EA of the forward reaction, is going to be 42.5 kilojoules. Okay, how about our activation energy, but for the product, okay, in the reverse direction? So now we're just trying to find this going all the way down towards the product. What would we get? Okay, so we're again at 80. Okay, up here is going to be 80. So let's find our reverse this time. Let's do our 80. Subtracted by what? Our product. Look at what we determine our product was. It was 12.5. So I'll write it over here. Okay, so you're just going to subtract them. What do you get? Okay, I end up getting 67.5 kilojoules. Okay, so this here is going to be our EA rev, EA forward, and obviously our delta HR, which we've already found out. I can just list it here again, is going to be our 25 kilojoules. Okay, but remember, it is exothermic. We've released that, so it's going to be a negative 25 kilojoules. So is the reaction exothermic? Obviously, right, because our product have lost the energy. All that energy got released in that process in order to go down here, right? That potential energy cannot just, disappear. It obviously went somewhere during the time it became a product, so it obviously got released as energy, hence why it is exothermic. So I'll say here, therefore, is exothermic. All right, let's try this question then, okay? The molar enthalpies of combustion for the hydrocarbons in table 5.4. This here is in reference to the table 5.4, the combustion molar enthalpies. Right, A, the balanced thermochemical equation for the combustion of methane. Okay, so we have CH4 over here. This is going to be a gaseous compound. Okay, we're going to add this with oxygen. Obviously, it's going to be gaseous. It's going to release CO2, obviously gaseous, and H2O, obviously going to be gaseous. Okay, now it says to write a balanced thermochemical equation. We have to find it for CH4, so we can find our CH4, our methane over up there, and as you can see, I'll do it in a little bit in a different color here. As you can see over there, it is 890.8, okay, kilojoules per mole. So again, it's negative, so we have to put it on the product side, okay? So we're just going to put 890.8 kilojoules, and again, there's only one mole that we can see so far. Actually, to bring that up, we actually have to balance this out quickly. I'm pretty sure it's going to stay as 1 mole, but give this a try. Quickly balance it out. What do you get? All right, so this is what you should have gotten after you've balanced it out. So like I was saying, it should be per mole, but this means this 890.8 kilojoules, it's going to be on the product side. That's why we didn't put a negative symbol. Okay, please look at my video for the representing enthalpy. And then this here is methodology number 1. Just rather than putting a delta H value at the very end here and listing it as positive or negative, it's always going to be positive, but it'll be positive if it's on the product side. So it's going to be negative if it's on the product side, or it's going to be positive if it's on the reactant side. Okay, and obviously in this case it is negative, so it's going to be on the product side, but represented with a positive symbol. So this here is our balanced thermochemical equation. We've done that, so that was A. So now we're going to do B, draw a potential energy diagram. So if I were to draw this out like this, Okay, draw a potential energy diagram that reasonably represent this combustion reaction. So obviously here we have our CH4. Okay, and we got to add it with our oxygen. Okay, and as we go up, and this is a combustion reaction, so it requires lots of energy, right? Because in order for it to combust and ignite, we would also have to put a lot of energy into it. So let's just go a little bit higher, and as it goes down, we know that this is exothermic, so the product is going to be a lot lower than the reactant. Okay, and this is going to be our product, CO2 and H2O. Okay, so we've pretty much done that. Again, we have our potential energy on the side, our reaction progress on the bottom. But then what is question B asking as well? Okay, indicate the delta H comb. Okay, we've already indicated that here. Okay, and a molecular structure that could represent an activated complex. Okay, remember, activated complex is up here. This is where the bonds are broken or formed. Okay, whether it precedes or not the reaction. Okay, so what do you think we would put up here? Well, we would actually put our reactants. Okay, because even though there is a chance that it could go backwards and not have the ability to proceed, there is a chance that it could be unstable here. Maybe I'll write this here. It's unstable. Okay. However, if it does have that sufficient amount of energy and correct molecular geometry orientation, and those both suffice, it could proceed and then become these products over here. So we're just going to still put this, I know this is our reactants as we see here, but we still have to put it up here as well because we don't know what could happen. This next question, when steam is passed over a hot iron, a reaction occurs as shown below. The activation energy for the reverse reaction as EA rev is 200.71 kilojoules. Okay, so let's quickly draw this out so that we can illustrate it. So we're drawing it out like that, and then of course same thing, our P is going to be on the side, reaction progress on the bottom. Okay, calculate the activation energy of the forward reaction. Okay, well, first of all, we need to check whether this is going to be a rough drawing, if it's going to be exothermic like this, or if it's going to be more endothermic like that. Well, we can already tell here that our delta HR, okay, our enthalpy change, okay, so the release of energy here is going to be negative value. So of course it's going to be our products that are going to be smaller. Okay, so in terms of potential energy, so if we were to find the difference between this reactant over here and our product over here, this is going to be our 151. So maybe I'll put delta HR. Delta HR is equal to 151, okay, 0.2 kilojoules, but it's negative, hence why our product is lower. And the activation energy for the reverse reaction is 200.71. Okay, so how would we figure this out? Well, our reverse reaction is going to be in the opposite direction, so it's going to go up this way. Okay, so this up here, okay, our activated complex is going to be that target, okay, of 200.71, but we're starting as a reference point where our product is. Okay, so if our product is over here and we have to find the activated complex all the way up there, right? This means this whole line over here, this vertical line, is going to be 200.71 kilojoules. I'm just going to kind of draw it here on the side here. Okay, this is 200.71 kilojoules in reference on the side. Okay, and then we have to eventually find the activation energy of the forward reaction. So we have to now find this one over here. Okay, because this here is the activation energy of the reverse reaction. This one over here, we need to find the activation energy of the forward reaction. Okay, right over here, the difference between this product line and this one over here is 151. So maybe I'll write this here. This will be 151.2 kilojoules. Okay, in order to find the difference, okay, it's going to be between here and here. So you just do a calculation of 200.71 minus 151.2. That's going to give you the answer. So I ended up getting 49.51. Okay, so 49.51 kilojoules. Okay, so that is our activation energy of the forward reaction. So draw labeled potential energy diagram, which I've done over here, showing the enthalpy change, which I've done there, activation energies for the forward here, and activation energy for the reverse reaction. This is complete. Right, so these here are our green questions of the day. Please give this a try on your own, pause the video, and I'll be giving you the answers shortly. This is the answer to the first question. This is the answer to the second question.